are the fundamental type in C or C++. So you don't need any libraries to support arrays. And today we are going to talk about character arrays. Right? Character arrays is similar to all the other arrays. The only difference is this guy is the string, right? The old C string. So you can directly print it or output it. And you can also think of it as a typical arrays, right? You can carry out many operations on every characters that is inside this this array. And we said if you use single quote, it is a character. If you are using double quote, it's a string, right? So a typical string is like this. First, it's type, right? Character, array. Then you assign, for instance, hello to it. So one tricky thing is if you see 5 characters here, the size is indeed 6. The size is indeed 6. And if you look at how it is stored in the memory, it's stored like this, HELLO, right? Then a \0. You have to specify when the string stops, right? Because everything is an ASCII code. If you guys can remember, H is a, if you look at the ASCII table, H has some number, right? E has some number. So it's very similar to some integer arrays, right? If you don't specify where to stop, when you're trying to print, this greetings, this character array, right? Your function don't know when to stop. So let's try it. Let's try it in this way. First, we have learned how to define an integer array, right? For instance, we can initialize it using 1, 2, 3, 4, right? Then we know the size of the vector. Let's call it array. The size of the array is 4, right? We could also do the same. Let's call it a string. H E E no L L O. In this way, this character is size 5. The size is 5. If you are defining it in this way, the size is 6. So there's a little bit difference, right? The first one, you specifically define a character array in this way. In the string 2, you are giving a string to the character array. Then how about let's try a print, right? So the benefit of defining a character array is we can directly print it, right? We can print it and it will show us the strings. But we cannot do it for the int array. If you print it in this way, it's printing this address, right? Like we said, the array name is the address that is pointing to the first location of your array. Then how about we print string 1? Not string 1, just a string. How about this one, right? We specifically define it as HELO, then print it. What will happen? It has some weird things, right? We not only print hello, because the next item might not be \0, it will keep printing some weird numbers, right? And at the end, it will stop when it meets some 0 to it. So we have to put a 0 at the end so that it knows when to stop. So if I write it in this way, string and string 2 are exactly the same. Then it knows when to stop because we have a \0, right? So if you print it, you will see a hello, hello, right? So these two are these two are exactly the same. It has to be put a \0 at the end. And also, what you can do like this, right? \0 is also the ASCII code 0. If you put ASCII code 0 here, when you convert it into a character, it will becomes \0. \0 is a character, right? So, right? Assuming this is our memory, when we specify this string in here, str, right? Give it a bunch of, it's an array. Then we have HELLO. It is indeed ASCII code stored, right? In this memory, it's just some numbers. After it, if we don't specify this \0, after it, there may be some random numbers, right? Maybe a 10 here, maybe a 20 here. But in most cases, right, many of the places in our memory, there will be some 0 here. If you didn't specify the next, the character after your O is \0, it might be some random number. So when you print your string, you print HELO, then it will look for the ASCII code for 10, look for the ASCII code for 20. Then when it meets 0, it stops. All right, so that is how the print is implemented. So people have implemented the print in this way, right? It's print every character one by one until it meets a 0. So if you want to print a correct string, if you want to define it in this way, you have to put a \0 in it right after all the strings. And also you can put something in the middle, right? If I put this one in the middle, HE \0, O \0, and if you want to print it, you will only see HE. So it will print from the beginning to the end and keep printing until it meets a \0. It will stop printing. Right, so that is the string. So let me make it back. So the string and the string2 in this way, these two are exactly the same. These two are exactly the same, right? So this is very important. Remember to put a \0 at the end, right? If you are assigning it in this way, it will automatically put a \0 to it. So your size would be 6 instead of 5. So that is the difference between integer array and string arrays. And also we have a specific function to compute the length of an array. We said the reason we prefer vector because vector can call dot size, right? So for this ARR, we cannot get the size, right? We cannot get size like this. For a integer array, we cannot get the size. But for a string array, we can get the size because we know the size ends with \0. So we can iterate through 1, 2, 3, 4, 5 until we meet a \0. So we can get the size, right? We don't need to remember use a specific variable called a size to it. We can automatically call a function which is string length. This function. And this function, I believe, is defined in the C string library. This is the old C library. C string is the old C library. And in their C library, they defined something called string length, which can compute the length of a string, right? Let's compute it. And print it. As you can see, it print size 5. And the size is the size you see. Hello, HELO, the size is 5, right? What if I put a \0 in here? What it will be the size? What would be the size? Yeah, it will stop whenever it meets a \0. So this is the, let's try this way. Let's try make it here. It should be exactly the same. String length 2. So it will compute how many characters before \0, right? So string length is implemented in this way. String length. I read it here, but indeed it's already written by the C library, C string library. All right. I put it here just for you to better understand how this one is implemented. It's basically a while loop. Right? It's look at each character Si. You have a character array, right? Then you look at every character until you meet a \0, right? Then you will return the size. So this is the function that is already implemented. It can compute the size of a string, right? And also we said we can directly print a string, right? Directly print a string because it knows it will stop with a \0. But you cannot do that for a integer array. If it's an integer array, it will output the address instead of all the content because it doesn't know when to stop. Right? It doesn't know when to stop. You don't have the size information. You cannot automatically do this. So that is the tricky part about the character arrays, right? And next, if we ask you, okay, what we will input, for example, the maximum length is 4, right? If I told you the maximum length is 4 and ask you to store the content into some character arrays, you have to define your character array and adding extra size, right? This extra size is for \0. So that is the usage of a defining a character array. Let's do this exercise. First one is in our OJ system as an exercise, right? Converting all characters to uppercase. Right, this one, let's do it. So let's call it a upper. Our input is a character array, right? Character array, let's call it this way. Because we want to modify this character array, we don't put a const here. If I put a const here, it will be a read only. We cannot modify it, but we want to modify it, right? And then in here, let's delete all the other part. Just defining a new string, which is called, right, like this. What I want to do is, first I want to convert it to uppercase, then print it to see if this guy is correctly printed. Right, so now I need to implement my upper function. We said, because it's a string is just a character array, we can manipulate every characters, right? We can, for example, we can do something similar to integer array. Equals to 0, I less than the size, right? The size is string length of string. Then we can manipulate every character, right? This is the one character, so we can manipulate it. How can we convert a character from lowercase to uppercase? Adding 32, right? Or some number like that. So this is the way. This is the way we can convert from, wait, if it's a plus, we are converting from lowercase to, from uppercase to lowercase. If it's minus, we are converting from lowercase to uppercase, right? This is the way we do it. And indeed, we need to test, is this guy between A and Z, right? If it's capital letter, we do this. Otherwise, we don't do this. So this is the basic step to convert from lowercase to uppercase, right? Let's try it. wait a minute. It's minus. It's between A and Z. Then we do a minus. Oh, wrong. If it's A and Z, if it's lowercase, we do convert. Right? So in this way, we are converting it to uppercase. It's basically what we have learned in our maybe first or second class. How can we convert a single character? Now it is a single character, right? Ith element of your string, which is a character. And for this character, if it's between lower a and the lower z, then we can minus the distance so that it can be converted into uppercase. So for this one, it's not that hard, right? Because the only thing you need to know is about how to get the length of a string. This is the way you get the length of a string, right? Instead of, for example, call string.size or something like that. So any questions on it? All right, so next exercise, how can we concatenate two character arrays? What is concatenate? Let's do this way. First, we define a string one, right? Let's do this way. This is we define a character array with capacity 100, and we allow the user to see into our string. Then we do a new one, string 2. Then we allow the user to see in string 2. Then what we are trying to do is, how about we define a string 3, for example, a large size, and we call concat string 1, string 2, string 3. And we are trying to combine string 1 and string 2. And then we are trying to see out string 3. Right. So this is our goal. First ask the user to input two strings, which is limited by the capacity 100. You cannot input characters more than 99, right? Because we have one extra space for \0. And then we are trying to combine them, put it into our string 3. This is the function we need to implement. Then we output it. All right, let's do this. Concat. So let's call it concat. This concat has 3 arguments. First one, second one, and the last one. So let's write some comments here, right? Concat means string 3 equals to string 1 plus string 2, right? So we are trying to combine them together, becomes one string. So how can we do that? A bunch of for loops, right? We can manipulate every characters. So it's like for int I equal to 0, I less than string 1, its length, string length of string 1, plus I, string 3, I, assigned as string 1, I. So we are basically copying all the characters belonging to string 1 to string 3, right? If you think of an array, right? If you think of it as an integer array, right? If it's integer array, you're basically copying every element, right? This one is similar here. You're copying all the characters from one place to another place, exactly the same as the string or integer array comparison. And then what we can do is we copy the remainings, right? We copy the remainings, string 2. Then we are copy them one by one. but this one cannot be string 3i, right? Otherwise, it will start with 0. It will overwrite what you have already written in here. So this should be I plus, yeah, string length of string 1. Does it need -1? Let's try it. So assuming string length 1 is HE, all right? String length 2 is LLO. Then in the first for loop, string length of string 1 is 2, right? So this is our string 3. This is our string 3. The first element, when this I equal to 0, we are copying this H to here, right? Copying string 1, 0 to string 3, 0. Then I equal to 1, when I equal to 1, copying E in here, right? Copying E in here. Now when we go to this loop, this one ends string length 1 equal to 2. So this guy is 2. If it's 2 minus 1, this one becomes 1, right? Then if I equal to 0, this one becomes 1. So you are overwriting this element, right? So you have to be careful about whether this one is about string length or string length -1. All right, so let's assume this -1 doesn't exist. It is I plus 2, right? So next item is here. We will copy string 2's 0, string 2's 0 to string 3's 2, right? Because I plus 2. They will offset by 2 positions. So it will becomes L, then O, right? So when the loop ends, when this loop ends, we will copying all of them in our string 3. What need to be done next? What's our next step? Yeah, you need to put a \0 in here, right? What is this position? 0, 1, 2, 3, 4, 5. This is a 5, right? So in this position, you need to put a \0 here, which is string length 1 plus string length 2. So that is what we needed to do. So at the end, string length 3, string length of string 1 plus 2. We assign a \0 in here, right? Then we are done. We are concatenating 2 strings. So let's test that. First is C in and C out. All right, it's waiting for me to give input. HE, O. Wait, one is missing. Oh, I forgot to delete this guy, right? It's overriding this E. All right, so let's do it again. HE, O, right? My input is 2 strings. And then it concat these 2 strings and it becomes 1. So that is how you can manipulate these character arrays. All right, so any questions on this concat? So very important thing is don't forget this \0 at the end. If you want this string to stop here, you put a \0 in here. All right, let's continue if there's no problem. The last topic about arrays is similar to vectors, right? We talk about vectors, then we talk about 2-dimensional vectors. Similarly, we talk about arrays, we talk about 2-dimensional arrays. So it is exactly the same as the vectors, right? This is the row index, this is the column index, and we can access one element. And the beautiful thing you can see here, it is put by row, right? So the first difference between array and the factor is, we said factors allows any dimension, right? Because it's just a factor of factor. So the first row can be one size, second row can be another size, third row can be another size. That is a factor of factor. But if for a two-dimensional arrays, we write it in this way, it has to be a square or it has to be a rectangle, right? It cannot be any size. If I say 11 by 6, the rows are 11, the columns are 6, right? It is fixed. You cannot change. For example, the first row is 6, second row is 5, third row is 7. You cannot do that in the C-style two-dimensional arrays, but in factors, you can do that. So that is the difference. So if you are trying to see how it is the layout in memory, this is like this, right? The array name, this array name powers is still an address. It's still an address pointing to the first location of your two-dimensional array. And then you will put first row first, right? First row first, you put it in your memory, then second row, then third row. It is exactly the same as factors, right? You put first factor, then second factor, then last factor. And if you want to access powers 3, 4, right? If you want to access this one, compiler will change this code such that it will be able to find out where is this location. So compiler will help you to find out this exact location. In order to find it, what kind of information do you need to know? Consider this is just a bunch of data. This is your memory, all right? This is your memory. There's no information about rows or columns. There's no information about rows and columns. The only thing you know is the starting position, which is powers, then index I and the index j, 3 and 4. How can you find out where this location is? Basically, you need to count, right? How many elements are before me? For example, before me, there are 3 rows. So it should be 3 times columns, right? Plus 4. So in order to find out this exact location, compilers need to know the columns. 3 times columns plus 4. And also it needs to know the type, right? Because it knows the type is double. Because it's double. It knows it needs to jump. Each double, for example, is 8 bytes, right? It needs to jump how many bytes? Then it will get the data. So the column information is very important for the compiler to find out where this data is. Let's see here. This is how we can pass a two-dimensional array as a parameter to a function call. Let's copy that. Let's copy it here. Make it this way. All right. So as you can see, we can let me comment them out. Put things here. So first, how can we define a two-dimensional array? It's like this, right? For example, 10 by 10. It is a two-dimensional array, right? It's 10 rows, 10 columns. Let's make it easier to see. Constant int rows equals to 10, columns equals to 10. Then we can have a rows and the columns, right? For example, if we want to assign some data to it, we can use our things similar to our vectors. I less than rows plus I. Wait. This part, yeah. For int j equal to 0, j less than columns plus j. Assuming we want to assign table ij as I times columns plus j, right? I just give the element to each, give the value to each element of the table. Let's see how it works for the print function. Print our table. I need the columns. No, I need the rows. Rows, right? Yeah, I need the rows. If you print it, it's too much, but it's, yeah. Let me make it smaller. 3 by 3. Then I need to change it to 3. Change it to 3. All right. So this is the table, right? I first define a 3 by 3 table because we said the size need to be known during the compile time, right? Then we give it a constant rows and a constant columns, and then we assign values to each one of them, and then we print it. When we print it, as you can see, the table is passed by address, right? Table is passed by address. So in here, you will get the exact address as the outside table, as this table, and we give it number of rows. So we put a number of rows here, right? This is iterate through all the rows. This is iterate through all the columns, and we see out it and give it a new line. So in here, there's a little bit tricky thing. First one, we put a 3 here. How about we delete it? What will happen? The compiler will complain. Compiler will complain if you don't give the size for the columns. Why is that? How about we put a column here? The compiler will still complain. The compiler will still complain, incomplete. This guy is incomplete because we said if we want to access table ij, they have to know the column of table, right? The table is a continuous memory, and the first one, first row 0, then row 1, right? If we want to access this guy, this one is the I times plus j, right? This is this element starting from the table. This is the first element. This is the table, which is the starting position, starting address for your 2-dimensional array, right? If you want to access a specific element, you need to calculate the I times columns plus j, then you can compute, okay, this is the element you want to access. If you don't know the column size, right? If you don't know the column size, compiler will never know how to access this data. So you have to give the column size to this function call. And you would ask, okay, I put my column here, right? I put my column here. How does the compiler doesn't know that? It can be converted into something like this. The reason is this is just some parameter. You can give any name to it, right? Compiler doesn't know this guy is his columns. He doesn't know that. It just the function parameters, right? It doesn't belong to it. It doesn't belong to it. They are two independent variables. These guys are two independent variables. So when it's trying to do this, it's still trying to figure out what is the columns, right? So you have to give the column size to your function call. For example, if we put 3 here, it also has one extra problem is you are making this function call less useful, right? It can only work for a 2-dimensional array whose columns are 3. If your columns are 4, for instance, if your columns are 4, when you call this one, when you call this function, let's put a 3 here. When you call this function, as you can see, this function, it says the column size for this table has to be 3, but you are giving a table whose columns are size 4. it will say, okay, there's no matching function to call for the print because this table doesn't fit this table, right? Because the column size doesn't fit. So it will make the make your program less useful. So one thing to do it is you can define a global variable. We will talk about global variable in the future. You can define your columns here, right? For example, you define a global one, columns, which is equal to 3. Then you can put your columns here, right? And then you can delete this part. Yeah, now it matches because your table, which is columns, is a global variable. This global variable shares with this print function. So these two guys will match with the column size. This is the one bypassing. So another part which we will discuss in the future is about using pointers. So because we know table is just an address, instead of doing this way, what we can do is we can make this guy a pointer. It's indeed a pointer pointing to some pointer, right? Because each array is a pointer. Yeah, I don't want to confuse you in here, but in the future we will learn this, right? And using that one, so we said in order to fully understand arrays, you have to understand pointers, address, and many things. So we would suggest you to use vectors instead of arrays for now. And in the future, when you learn pointers, you will get a better understanding about these arrays. And especially, arrays are very useful when you learn about the dynamic allocation. So if you want to create a size of array which doesn't know the size in prior, so you should use the dynamic allocation. But that's all after the pointers. So I just want to introduce arrays in here. So for all the remainings, you guys can go back and see it after the pointers class. Yeah, so let me go to next part, which is recursions. Recursions, so first is about what is recursions, right? So recursions is a thinking method. We say a thinking process of how to solve a problem. So recursions is just function calls. The only difference is function call needs call itself, right? It's like you are trying to build a hammer, but you need a hammer to build a hammer. And then how can you use a hammer to build a hammer, right? So that is the recursions. So especially when you are trying to implement something, it's very confusing. I haven't finished this implementing this function, right? How can I use this function before I implement this function? So that is the confusion you will have. So the more important thing is about how to think recursively. For most of the problems, you don't need the recursions because the recursions are quite slow. We would prefer a loop version, right? If a while loop, for loop, it will be a better way. But I would teach you how to do it recursively. It's just a practice, all right? Most of the examples I use can be done in loops. So first is a very simple example, factorial. Let me go to that one first. Let me introduce you the key ideas about recursion. So for instance, when we are trying to, for example, prove 1 plus 2 plus ... plus n equals to n plus 1 divided by 2, right? If we are trying to prove this one, we say, okay, first, we have a special case. When n equals to 1, it holds, right? Left side is 1, right-hand side is 1 times 2 divided by 2, right? Then we are doing induction, assuming it holds for n equals to t minus 1. Let's prove for n equal to t, right? So it would be 1 plus 2 plus ... plus t minus 1 plus t, right? Because we have assumed this guy, right? It holds as the formula shows here. So we can replace it with the formula, which is t minus 1 multiply t divided by 2 plus t, right? And then we can get to t plus 1. So it basically says, first one, we need to prove for the special case. If for the special case it's correct, right, then we are starting from step by step. First, we prove, we assume this one is correct for t minus 1, then we prove it correct for t. So this is the main thinking process of recursion. So if you think of recursion in here, right, this one is a for loop version, factorial, which is, wait a minute, let me implement that one first. Recursions, right? Recursions, so how about we want to compute sum from 1 to n, right? And we define n, for example, to be 10. Then let's, yeah, we need to return an integer. How can we do it? We said special case first, right? If n equal to 1, we will return 1, right? Let me put a comment here. Return sum of 1 plus 2 plus dot 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 plus n. If n is 1, we return 1. It's a special case, right? Then we will get a smaller version, which is sum of n minus 1. When you write to here, there's some struggling points. Implemented sum function yet, but I start to use sum n minus 1. Right. So this is the think recursively. You just assume it works. You just assume this sum function works for n minus 1, right? Your next step is how can you construct your result from this smaller result? So it should be return smaller plus n, right? So that is the thinking process. Deal with the special case first. Assuming it works for a smaller version, assume it works for a smaller version, then using the smaller version's result to construct the result for a large problem. So you can run it to see if it works, right? 55, it works. So this is the think recursively, right? Let's do it for the factorial. So factorial is n factorial. If you do it in a for loop, it's starting from result equal to 1, then a for loop I from 1 to n, right? And multiply into the result each time. So this is the factorial. So we could also implement factorial. We could implement factorial in this way, right? Let's call it fact. First, if n equal to 1, we of course return 1, right? Let me put it here, return 1 times 2 times until n. So these two are quite similar. And we can have a smaller result, which is a factorial of n minus 1, right? And at the end, we return a smaller version times n. This is the factorial, right? These two are exactly the same with each other, except for the multiply versus plus. And what we can do is we can see out this fact, n, right? Then we will be able to get the result. So that is the thinking process. And the more important thing is you know how to debug. Let's make it 4. Delete this part. Let's debug this factorial function. How can we do that? We create a breakpoint, we run to it, then we jump into it. when you first get into this function, this n is 4, right? You are in the fact4 function. Then when you go one more step, it will cause fact3, right? N minus 1 is 3. Then if we run it, it will jump into your fact function with n equal to 3. Then we will go this line again. It's not equal to 1. We go to next. Then it will call fact2, right? Then when we run it, we are inside another function with fact2. In fact2, it's still not equal to 1. We will call another function, which is fact1. Then we jump into it. We are inside the fact1 function. And if you check your debug, you will see it creates many versions of factorial functions, right? And when you go it here, because it now n equal to 1, right? Now n equal to 1, it can return. So next step is returning. Now it's returning. We are returning to the function called fact2. And because fact1 stops and returns a 1, it will be assigned to this smaller. Now it's 0. It haven't been assigned yet. Now smaller is assigned with 1. And then we will returning 1 times 2 times 2, which is the result of fact2, right? Then we jump out. We are inside here. It haven't been assigned to smaller yet. We run once. Smaller is 2. We are inside the fact3 function call. And then we are returning 2 times 3, right? Then we are returning 2 times 3. Now fact3 is done. We are assigning to smaller. Smaller haven't been assigned yet. Now smaller equal to 6, which is fact3. And then because we are in fact4 function call, so it will returning 6 times 4, right? And then when it goes out, it will be here and it will be printed 24. So the whole process is like this. Let me create a new one. The whole process is like this. We have first a function call, right? Function call, this one is called fact4. Inside of fact4, you have a variable called smaller equals to the result of fact3. Fact3, right? Inside of fact3, your smaller variable equals to the result of fact2. In fact2, you have a smaller variable which is assigned to fact1. And in fact1, it returns a 1 here, right? Returns a 1 here. And here returns 1 times 2, which is returned to here. And then this 2 times 3 returned to here, right? Then this 6 times 4 returning to the outside. So this is the whole process of recursion, right? You are basically the factor function calling another factor function, calling another factor function. So when you are in here, right? All these 4 functions exist. They exist, right? They are inside your memory. All these variables, so all these functions, they exist, and all of their temporal variables, they are independent, right? Yours called smaller, mine called smaller. They are different variables. And this is the process. So let's look at how it is done in here. Let's see. All right, let's do it step by step. First one, we need to write down our solutions in this way, right? N factorial equals n minus 1 factorial times n, which is, if you think of factorial as a function, fact n equal to fact n minus 1 times n, right? This is the way we're writing down as a recursive solutions. Then we need to deal with this special case. If n equal to 1 or 0, it returns 1, right? In here, I just write the n equal to 1 version. You could also add in the n equal to 0 version, just in case people ask you to return a factor of 0. And then you can write it down. Your functions like this, right? Smaller factorial equal to factorial of n minus 1. Then you multiply them, becomes the new result. And then you return it. So if you look at how it is computed, right? This is exactly what we have done. First one, we call this function with a factorial 4. Inside of factorial 4, we call a function called factorial 3. Inside of factorial 3, we call a function called factorial 2, right? This indentation means a function call, right? And then when it returns, it goes to factorial 2, then go to factorial 3, then go to factorial 4. So, so one bad part about recursion is debugging this kind of code is quite difficult because you have too many function calls. Debugging it is very, very hard. So for this kind of simple cases, for this kind of simple problems, constructing from a smaller result, easy, right? For a smaller factorial, you construct with a large factorial, you just multiply by n. It's not the case for all the recursion problems. It's just for this kind of simple questions. For simple questions, constructing from smaller to large result is easy. But for more difficult problems, this part you need to pay attention to it. All right, so recursion is the technique of expressing a solution in terms of a smaller version. So a smaller version sometimes means a smaller number, right? A smaller number, which is the n minus 1, right? Sometimes for strings, it can be size 5, now becomes size 4, now becomes size, for example, not size 3. And also for example, for a range, right? For a range, then becomes a smaller range. We will show that. And there are a few techniques, right? First one is how to express your problem in recursive way. Second one is there should be some special case you can deal with so that your recursive will stop, will terminate. Otherwise, you just keep on and on and on, right? It will never stop. And also, we say it will call itself again and again with smaller and smaller values. Eventually, it will reach the special case, for example, 0 or 1. So let's do a Fibonacci. This one, right? How can we write a recursive function to compute Fibonacci of n? Fibonacci is every element, like the 3, is the sum of 2 previous elements, like 3 equal to 1 plus 2, 8 equals to 3 plus 5, right? So it is indeed growing very fast, but we only shows the first 10 elements. So let's do it together. Let's call it Fibonacci int n. Right, if you can still remember, n is 0, 1, 2, 3, 4. Then fib is 0, 1, 1, 2, 3, 5. 0. Yeah, is it correct? Let's see. Yeah, it's correct. Let's put one more. If 0 is this, n is this, then yeah. So here, let's start with the easiest case, right? How can we write down it using the recursive way? How can we express Fibonacci of n recursively, right? First, we said we want it becomes a smaller problem, Fibonacci of maybe n minus 1, right? By definition, it's indeed n minus 2, right? So what we are trying to do is we are returning plus Fibonacci of n minus 2, right? This is something we need to do. But we said it will never stop, right? If you give it 0 here, it will equal to Fibonacci of minus 1 plus Fibonacci of minus 2, right? Then Fibonacci minus 3, then Fibonacci of minus 4. So you have to ask it to stop. For example, if it's n equal to 0, return 0. Is it enough? Yeah, you still need a 1, right? Because otherwise it will go to minus 1. You can try that, n equal to 1, right? Then it will be done. Let's try it. Fibonacci of 4. How about that? Oh, I create a breakpoint here. Let's delete this one. Fibonacci of wait a minute, because it's returned. No, it's not correct. In that case, it will be all of them will be 0. If n equals to 1, return 1, right? To special case, I make it wrong. And when it's 4, 0, 1, 2, 4, when it's 4, the answer is 3, right? When it's 6, the answer would be 8. The answer would be 8, all right? So as you can see, one function call becomes 2 function calls, right, to itself. So Fibonacci is using recursive way is very slow. You can test it. You can test 100. Try it. It never stops. It never stops. It's still running. It is still running because it's too much. Let me close it. Let's make it 20. Let's see how long does it take. Oh, it's quite fast. 50. Yeah, it takes some time, right? It's still running, as you can see. It's using my CPU, 99% memory, and so on. So in this way, it's quite slow because each one function becomes 2 Fibonacci function, a recursive function calls. And in next class, we will talk about the efficiency because it's growing, doubling each time, right? Doubling each time. It's almost close to 2 to the 50 number of function calls. So that will be quite slow. How can we make it a loop version? How can we use a while loop, for loop to do it? How can we do that? Let's call it iterative version. So iterative means a loop. This is recursive. This is iterative. You have to remember the name, iterative. All right. Let's see. First, let's do the special case copy here. Let's just copy the special case here. All right. Assuming n is greater than equal to 2, how can we do that? There's a technique. It's called sliding window. Assuming we have already know, for instance, 0, 1, 1, 2, 3, 5, 8, right? If we have any place we need to compute, we need to remember what is your previous one, what is your previous one, right? These are the 2 you need to remember. Then let's call it current. Your current equals to previous plus previous, right? After you finish computing this guy, you slide it. You go to next part. Let's change the color. You go to next position. Now this guy becomes your current. What is your previous? What is your previous? This is your previous, right? So it has to be previous becomes current. And then what is your previous? Here is your previous, right? Previous guy, which is your old previous. So it's called sliding, right? You are sliding it by one position, then sliding it by another position. So you need to do it by hand, then make it some code you can write down. Let's do it. We have 3 variables. First one is previous, then previous, then current, right? Let's do a for loop. Let's give the previous some initial value, which is 1, and the previous equal to 0. These 2 are, this one is n equal to 0. This one is n equal to 1. Now we are trying to compute your current, which is n equal to 2, right? Let's forget about a for loop. Let's compute n equal to 2, which is current equals to previous plus previous, right? Because this previous is n equal to 1. This previous is n equal to 0. How about n equal to 3? We're sliding it, right? We are sliding it. And for n equal to 3, your previous is indeed this current, because this current is n equal to 2, right? And then your previous is n equal to 1. N equal to 1, which is 1, becomes previous, right? Now you are moving previous and previous one step ahead. Then you can compute your new current, which is this guy, right? So for this one is n equal to 3. This one is n equal to 2. This one is n equal to 1, right? This previous is the result for n equal to 1. Let me make it clear here. Previous equals to 1. Previous equals to 0. So this guy is n equals to 0. This guy is n equal to 1. And this guy is n equal to 2, right? You are sliding it one by one, until you can reach the end. So if we want to make it a for loop, it's basically doing this, I less than maybe equal to n. You need to test it, plus I. It basically says, let's see what we should do. Yeah, we just copy it here. The current should be up front because we already assigned the previous yet. So for this guy is n, right? For this guy is previous is n minus 1. For this one is n minus 2, right? So you are trying to slide it and compute it. Let's comment this out. Comment this out. And to see whether it's correct, return your current one. Current may be uninitialized anyway. Let's try Fibonacci iterative way. Where is 0? 0, 1. If it's 50, why it's 0? I less than current previous assigned. Oh, wait, it should be the reverse. Because I overwrite the previous, right? So the old previous should be assigned to first. Otherwise, the previous will be the new current. Yeah, this one is correct because this number is too large. It cannot hold in an integer. You have to make it a long or some large numbers. But anyway, this one, as you can see, it's very fast, right? Whenever I click, it gives me the answer. The loop version, iterative version, is more efficient than the recursive version. So if you want to try it, don't try it with a too large n, right? If it's too large n, your machine will keep on working on it. So anyway, let's go back. This is the Fibonacci. You should learn how to convert a recursive to a simple loop. Tedious to write it, right? As you can see, you need to remember what is a previous, what is a previous. And you have to make it, so you have to think about it clearly. Otherwise, you will make some mistake. And we will revisit this one when we talk about the efficiency, right? Who is faster? Why is faster? So we will learn that. All right, so before we go that, let me introduce another technique, which is maybe the first algorithm we learned. It's called a binary search. What's the problem? The problem is assuming we have a vector sorted. And we are trying to find out a target. For instance, it's 8, right? Your job is to return the position for that number. Find it. Find the vector, the target. So this is your goal. You are trying to find out where is the position for 8, assuming the vector is sorted. It's sorted, right? One naive way is, of course, int find a vector, because we want to save some space. We reference because we don't want to change it. We put a const, right? And then we have a target. And in order to find it, a naive way is 0 I less than bc dot size plus I if vector of I the same as target, right? We return the position I. If we didn't find it, we return -1. So this is a very simple way to implement it, right? It's basically comparing them one by one and returning the position. But the question is, can we not doing this way, right? Because the vector is sorted. You don't want to compare them one by one. Can you make it faster? Can you using recursion to make it faster? So that is the problem. Let's call it a find naive way. All right, let's implement another find function. Let's use our thing here, right? First, we have our vector, which is sorted. 2, 3, 5, 2, 3, 5, 8, 11, 13, anyway. And we are trying to find out the 8. This is a recursive function. This is a recursive problem, right? You are trying to find out, assuming this is the start position. This is the end position. We know the position is in the range between start to end, right? This is a large problem. Can we make it smaller? The typical way would be, okay, how about I compare with the start, right? If the start doesn't match, our range becomes start +1 to end, right? This would be exactly the same as our naive position, right? Naive solution. We compare is the vector of start if this guy doesn't equal to our target, right? If this guy doesn't equal to our target, we are trying to search the remaining part. We are also making the problem smaller, right? The range is smaller. We can keep shrinking the range until we find until there's only, for example, one element in the vector, or there's no element in the vector. Then we are done. So this one is the naive version. What we want to do is, let me erase this part. Erase this. All right, so what is binary search? So binary search is we first find someone in the middle. Find someone in the middle, then we compare our target. If target is less than vector of middle. Because this vector is sorted, right? If our target is less than the one in the middle, we know the position should be in the range from start to middle -1, right? It should be in the left part. So each time you are making the problem smaller, which is making the range cut it by half, then cut it by half, then cut it by half. So there should be, so each time you are comparison with one element. So in total, you need log 2n comparisons, right? So starting from the size n, the total size is n. This size is n. Now size is n divided by 2. Next size is n divided by 4. you keep shrinking the size, right? Keep shrinking the range you want to search for until there's only one element. You don't need to shrink anymore. So the total number of comparison will be log to n. You don't have to know that. This will be introduced when you are learning the algorithm class. So this is something we need to implement, right? How can we implement this binary search? Let's do it. So let's just copy that. And we need a start position and a int start, int end. This is the range we want to find, right? Find target in vector in the range of start to end. So we can give it a start position, which is 0, end position, let's call it size -1, right? This is the last element. We search for the whole space. So how can we make it? Binary search? So first, let's do the easiest one, right? If let me first find out the middle one, the middle guy, which is start plus end divided by 2. Because start is an integer, end is integer, divided by integer is an integer, right? So we are comparing the vector of middle with target. If it matches, we return someone in the middle, right? Else, if this guy is less than target, we need to search for the right-hand side, right? So we need to find the vector with the target, the range. Range is middle +1 until the end, right? If in the middle element is less than target, we search for the right part. Else, search for the left part from start to middle -1, right? So these are the basic steps. As you can see, we are trying to make the range, searching range, cut it by half each time. And finally, we hope we can find it. As you can see, it can find the exact location, right? So there's one problem is if this target doesn't exist in this part, for example, if I'm looking for a 4, right? If I'm looking for a 4, this function will return a -1. What if I also wanted this guy to return a -1? There's only one case that this guy will stop, is when if start is less than end. No, wrong. If start is greater than end. So each time you are searching, you are trying to shrinking until middle +1 is exceeding the end, or start is greater than middle -1. Go back and check this part. Let's comment this out. Go back and check this. Return -1. Why this can work? Go back and check that, especially trying to find out middle +1 and compare it with end. All right. Let's see whether it will return a -1. Yes, it will return a -1. So if it doesn't exist in the vector, it will return -1. This special case, there are two special cases. First special case is your range is invalid. Your range is invalid. Your range is valid only when start is less than end, right? If start is greater than end, there should be nothing to search for. It should be a -1. It's invalid. And another stopping case is if we find the target, right? We immediately return this middle. So these are the two special cases. These are the case you are trying to make your problem, a large problem, becomes a smaller problem, right? Large problem is search for the target in this large range. Now you are becoming a smaller range, cut in half, right? Cut in half. This is a smaller range. So that is the usage of recursion. Of course, you can rewrite it using a for loop, while loop, right? You can rewrite it in a while loop. And yeah, I believe you guys can do that. Go back, convert this guy. Let's do this. Try to convert it into loops, or we call iterative version, right? Try to convert it into loops. If you guys can convert it into loops and making sure everything works correctly, then that will be good. So again, let's give you a hint. It could be a while loop, right? While start less than end, less than or equal to end. Then you do some work, right? It'll be very similar. But you still need something like this guy, using extra variables to remember the locations. No, maybe you don't. Yeah. Anyway, try that offline. I will upload this code into Canvas. So another problem, because I don't have time to do it, but I will do it in next class. But I just give you a hint and try back and implement it. All right. It'll be very similar to this one. Ask you to implement a function to compute the square root of n. Compute a function to compute square root of n. Let me give you the algorithm. Assuming this guy is x, all right, and then you have a function called fx equals to x squared minus n. You are trying to find out when fx equal to 0. Let's draw fx, right? This is x squared minus n. Let's assume n is greater than 1. So if I give you a 0, it's a negative n, which is less than 0, right? If I give you the n, this is n, go here, it is n squared minus n. It's greater than 0. First, this part is negative, this part is positive, because the function is continuous. Your root has to be in the range between 0 to n, right? Then you find someone in the middle. This guy called middle. Then we compute f of middle. If f of middle is negative, your root is in the range between middle to n, right? Seems similar, right? Exactly the same as the binary search. Each time you are making it smaller and smaller, smaller. And finally, when do you stop? When the range is smaller enough, you can stop, right? If the end minus start is less than, for example, 10 to the power of negative 10, if the range is small enough, you just output any number, right? In either start or end or somewhere in the middle, doesn't matter. So do this offline. It should be the same as this one, right? Quite similar. All right. So any questions? No? Okay, so see you on Saturday.